Okay, let's get started. So yeah, we're gonna upload our new lab and homework very soon. And if you finished lab 6 already, so I think you can start lab 7 tomorrow. Okay, so yeah, let's briefly review what we covered in our previous lecture. So in our last lecture, we focused on the non-ideal practical sampling, right? So for the lecture before, we talked about non-ideal reconstruction, right? So here is another part that we cannot implement in practice, so which is the sampling part. So in practice, so we cannot really do the impulse sampling, right? Like multiply the original signal by a delta train, right? So basically, what we can do is as follows. So basically, we have to integrate our input signal for some time, and then output the value of this integral. Okay, so this is what we can do in practice. So mathematically, we can represent it in either this way or this way, right? So this way may be better because we have a Q function. So that is device dependent, right? And so the Q function, this guy, may introduce some distortion, right, of our output, which may not be desirable. Right, so the way to deal with this problem is that, so first of all, we need to analyze what kind of impact of this Q function, right? So basically what we do is that we propose a frequency domain analysis, and eventually you can see the details in our literature, in our lecture, right? So we derive it using the entire lecture, which is a little bit longer than expected. So we get a closed form expression of this Fn here, right? Remember, if it's a delta impulse sampling, we don't have this Fn here, right? This Fn, the entire thing is a 1 over Ts, right? We don't have this for the ideal sampling, right? But now it's not ideal sampling, so we have Fn here, right? And this PF is a reconstruction filter that we used before, okay? And since we only care about the baseband part, right? Because we want to reconstruct our original signal G of t, right? So the thing that we care the most is F naught, right? For the higher order of n, we're gonna filter it out, right? Using a low pass filter, right? So for this part, F0 equals to that, okay? And so basically, so for the baseband part, so we have F naught multiply GF and then multiply our reconstruction filter, right? Remember, what we want is GF only, right? And with bandwidth of B, right? Then, you know, in order to get rid of the impact of PF and F naught, so basically we just need to divide it by itself, and then we're done, right? So using an inverse kind of operation. So basically, this is the idea for our design. So basically, what we do is that we want to make sure that we apply a filter after the operation, right? And in the frequency domain, you want to make sure that this filter will remove the impact of PF and F naught, right? So basically, it means that this multiply these two together will be equals to 1, but we want the time shift, right, in order to make the output signal causal. So that will be a phase shift here, right? And we only require that within the bandwidth of B, which is the bandwidth of signal, right? And yeah, I think this is a typo. So this should be Fs minus B. So when absolute value of F is bigger than Fs minus B, then it has to be 0. But in between, so we don't really care. It can be anything, right? So basically, this is our filter design, right? It's very straightforward, okay? So in many practical equalizer design, so we apply this kind of idea, right? The only thing we need to make sure is that, so Pf times F naught, this cannot be 0, right? If it's 0, then we cannot do it, right? So maybe not in this class, later for if you take more advanced communication theory class, like digital communication, so you're gonna see that, okay, when this guy is 0, then how can we deal with the problem, okay? So yeah, this is what we covered in our last lecture. Any questions? Okay, so if no question, maybe let's see what we're going to cover today. So yeah, we're going to show you some slides first. Okay, so this is what we're going to cover today. So first, we're going to talk about pulse modulation. And then we're going to talk about pulse code modulation. Okay, and then we're going to talk about the advantage of digital communication. We kind of discussed that before. Here, we're going to discuss it in a little bit more detail. And then we're going to see that, okay, so what are the desirable properties of the digital modulation? Right, and probably next class, so if we have a little bit more time on this class, so we're going to talk about line coding, so which is the simplest version of the digital modulation. Okay. Okay, let's see what is the basic idea of pulse modulation. Okay, so basically, so it is like you know the analog communication when we talk about amplitude modulation or phase modulation or frequency modulation, right? So basically, where we can use amplitude to represent information, or we use the phase or frequency to represent information. But here, so the pulse amplitude modulation, so basically we want to use the pulse shape to represent the information, right? For example, right, so this is a simple example, right? Let's say let's say this signal is our sample signal. Okay, so let's assume the ideal sampling, right? So now we can, you know, in order to represent the signal, so we can represent each of these points as a pulse like this. Okay, and then we're going to transmit this pulse. Okay, and as we can see that, right, you know, if we have this pulse, there's a way to recover the original signal, right? So this is called the pulse amplitude modulation, or PAM. So there are kind of other pulse modulation. For example, we have the PWM, so which is pulse width modulation, and PPM, which is a pulse position modulation, right? So basically, for the pulse width modulation, it basically means that the different ways of the pulse represent the information, right? So if it's wider, it may represent a higher value. If it's narrower, it may represent a smaller value, right? And so this, for the pulse position modulation, right? So basically, it means the position of the pulse representing information, right? Let's say the duration of a pulse is like this big, right? If, you know, with the pulse appear in the beginning of it, or in the middle of it, or, you know, or here, right? So the position of the pulse may be different, right? And this difference will represent the information. Okay, so so those are not commonly used in practice, but there are some advantages of this kind of modulation, right? Because yeah, similar to the FM modulation, right? For the PWM and PPM, so they all have the same amplitude, right? Which might be desired, right? So one big problem of the current wireless communication is that, you know, the signal can have very, you know, the range of the value of the signal can be very high, right? So this is not good, right? Because we have a range for our amplifier. We cannot deal with super high signal and a very small signal at the same time. Okay, and the disadvantage here for the PPM is that it is very difficult to keep the track of the correct symbol timing, right? Because the timing, the symbol, I mean, the location of the symbol changes all the time, right? It's kind of hard to track it, okay? So that's a disadvantage of it. Okay, and one big advantage of this pulse sampling is to do the time division multiplexing. So basically, it means that we can sort of transmit two signals at the same time, right? Like shown in this figure. Okay, and let's say this is one signal G1, and this is another one G2, right? So if they're analog signal, like, you know, this time, if it's a continuous time signal, right? So we can now transmit both of them all together, right? They overlap, they interfere with each other. But if we use pulse modulation, then we can transmit them together, right? Because, you know, there's no overlapping. Okay, so this is a big advantage of the pulse modulation. Right? Does that make sense? Okay, great. And And now let's see one very important pulse modulation. It's called pulse-coded modulation. Okay, so for the pulse-coded modulation, yeah, this is something that we use all the time in practice. So basically, what does it mean? What this means is that, so after the sampling, right, we do a quantization, right? So we kind of illustrate this kind of thing before, but now we're going to see what we exactly need to do, right? And let's say, so this is our sample signal, right? And then basically, let's say here we have 4 digits. 4 digits basically means that we can have 16 levels of signals, okay? Then we're going to quantize the received signal to these 16 levels, right? For example, let's say at this point the signal is, let's say the signal is here, right? But what we got is signal here, right? So corresponding to this point, right? If we have signal that is here, right? But we're gonna, quantize it to a signal here, right? Which is this point, right? So we're going to find the closest point to approximate the sample signal, okay? Obviously, if we have more digits here, then our approximation will be very accurate, right? So any questions? Okay, so first we do the quantization, okay? So this is the first step. Okay, after doing the quantization, so what we do is we have a bit encoder, okay? So bit encoder, basically, it means that, so we have the 4-digit, in this case, 4-digit representation of each of these points, right? And then instead of transmitting the value of this point, we're going to transmit the 4 digits here. Right? For example, if I have this point, then we're going to transmit 0, 0, 0, 1, right? And how to transmit this binary digit? Then there are many ways, right? So one way is to map each digit to some waveform and then just transmit it. Okay, so this is what we do. So let's see one example of it. So. Right here. Example of PCM. Right, so we're going to see a simpler example as we have seen compared to what we have seen in the slides. So basically, let's assume the analog signal looks like this. So that's G of t. Okay, so now let's assume that we have 3 levels here. Now let's assume we have 8 levels using 3 digits. What I mean, let's say here is 0, 0, 1 and 0, 1, 0 and 0, 1, 1, and we have some other digits here as well that I will not write all of them. So now the point is to do the quantization, right? Let's see what we're going to do here. Yeah, let's see, for example, let's see, we have, here 0, 0, and this is the first point, and here is the second point, and here is the third point, and so on, right? We have many points here. Okay, so now let's see what is the first one. Yeah, probably for this one, let's see the value is about here, right? So then we're going to quantize it to this one, right? So that's 0, 0, 1 for the first one. Right, and then for the second one, so we can see it is about here. So we maybe quantize it to 0, 1, 0. Okay, so basically this value represents this value here, right? And then for the third one, so we have value here, right? And then we can see that. Yeah, this is roughly around here. So the first one will be 0, 1, 1. right? Now clearly this one we're gonna quantize it to this one again, right? So 0, 1, 1. This guy may be 0, 1, 1 as well, and so on, right? So we have a we have a code book, we have a mapping, right? So basically, we know that when you see 0, 1, 1, it represents this point, right? When this point, right? When it's 0, 1, 0, it means this point. When it's 0, 1, 1, it means basically 0 point. Okay? Yeah, that's the quantization. So now, after this step, so we only need to transmit this binary digit. So we don't need to transmit the real values here anymore, right? So now let's see what we're going to transmit. Like for example, let's see the first three, like this, and that point, right? The first 3 points, we just need to transmit 0, 1, 1, and 0, 1, 0, and 0, 0, 0, 1, no, 0, 1, 1. And 0, 1, 1, right? So this is basically what we want to do here, right? And then, so let's see how we can transmit it, right? So basically, we're going to map this guy to some waveforms to transmit, okay? Because we need to transmit that over the air, right? We cannot just transmit a single digit over the air, right? So we need to map it to some continuous time waveform to transmit in the air, over the air, okay? So for example, we can do very simple stuff, right? So basically, let's assume that if it's 0, we transmit nothing, and if it's 1, we transmit a square waveform, okay? Yeah, maybe let's assume, yeah. Yeah, let's assume the duration of each of these digits is t, and so on. Right, then the first guy is 0, then we just transmit nothing. And second one is 0, we transmit nothing, right? And third one is a 1. Let's say we just transmit a square waveform like this. Okay, and the fourth, so this basically represents the first 3 digits, right? 0, 0, 1. Okay, and then we transmit nothing, and then we transmit a 1, right? And then we transmit a 0. Okay, and for the last 3 digits, so let's say basically here is, so this is 0, 1, 0. And then we have a 0, and then we have a 1 here, and we have a 1 here again. Okay, 60, 70, 80, and 90, and so on, right? So this is basically what we transmit over the air. Right, so now you can see compared to the original signal, right? If it's analog communication, so we're going to somehow transmit the value of the original signal, right? Either use amplitude modulation or phase or frequency modulation, but here, instead, we're transmitting all of these square waveforms, right? So this is a PCM. Right, does that make sense? So now you may imagine, okay, so why we're going to use PCM, right? So we're going to talk about the advantage of using that, but now let's see, there might be some disadvantage of using it, right? Can you imagine? So what is the disadvantage of using it? Right, I think the advantage is somehow, understandable. Yeah, because now before, transmitting, when we're transmitting this guy, it's very hard to get the exact value, at the receiver side, right? So, but now we only need to transmit this guy. So maybe it's easier to detect whether it's a 0 or a 1, right? So we don't need to receive exactly this to determine that it's a 1, right? So for example, if we see a higher value, yeah, it might be a 1. If we receive maybe just noise, maybe that's a 0, right? Seems a very robust way to communicate, right? So this can be an advantage. But what is the disadvantage? Yeah.
When you transmit 2 ones,
Uh-huh.
there's no way to distinguish between the time like you send one and then the other.
Very good. Yeah, we're going to discuss that later. That is it's a very related it's a topic. So basically, in other words, so basically you mean it's hard to determine when the signal starts, right? If we know the signal starts here, then we know how many ones we transmit, right? But yeah, that's totally valid. Yeah, that can be a disadvantage. Yeah, there's another one. Okay. Yes.
You can't shift your signal?
We can shift the signal.
Well, if you shift it, wouldn't it like completely mess up the values?
Shift it. What do you mean?
Like for the like analog signal, if you shift it, the signal would remain the same. But if you shift the bit system, it could like change the values.
Yeah, I understand. Yeah, it's totally valid. It's related to what the previous answer, right? So basically, it's hard to determine when the signal starts, right? So we don't know, okay, if it starts with a bunch of 0 here, right? So there's no way to know, okay, where the signal starts, right? Then, if it's shifted, we can determine maybe there's more 0 before, right? Yeah, that's totally valid. Okay, so yeah, let's compute something for this kind of signal, right? Let's see. It's kind of an interesting exercise. Let's compute the bandwidth of this guy. Okay, because we know the bandwidth of this guy, right? We assume the bandwidth of B is the bandwidth of this guy is either B or B half, right? So, and then based on our analysis for the modulation, so if it's AM, we know maybe it's 2B, right? The bandwidth, if but if it's a DSB signal and instead of B it's B half, then the bandwidth is B. Right, if it's FM, the bandwidth would be like how much? Some I forgot the formula. 1 plus this FM modulation index beta times the whatever delta F, right? So yeah, we can determine the bandwidth exactly for this guy, right? Roughly speaking, it will be either B or 2B, right? So, but now let's see what is the bandwidth of this guy. Right, we can determine that, right? Because we know how many samples we're going to get here by using the Nyquist sampling theorem, right? So now let's determine what's the bandwidth here. Okay, so basically this is the bandwidth of PCM. Okay, so we assume that our signal GT have a bandwidth of B. Okay, so if the bandwidth of GT is B, yeah, we assume that's a baseband signal, right? Bandwidth B, then it basically means that we need at least 2B, right? At least 2B samples per second to recover it, right? To reconstruct G of T, right? So I have 2B per samples, and so now let's assume that so each sample is quantized to n bits. Okay, then we could compute the bit rate, right? Then the bit rate must be greater than what? So every sample is n bit, and then we have 2 times b samples per second, right? So that's 2n times b, or maybe I can, yeah, 2n times b is good, bits per second. Right, so here by bits, I mean one bit is just one digit here, right? This is what we mean by bit, right? So bit can mean different things in different contexts, right? So this is what I mean by bit, right? For example, in this case, so each sample is quantized into 3 bits, okay? So n equal to 3 in that case, in this case, okay? Right, so is that clear for this one? Okay, great. Okay, so now did you remember? So we kind of compute that before, right? So I think maybe a few lectures ago. So when we talk about this sample signal, right? So we kind of talk something like very related to this, but not in this rigorous way, right? So we characterize that, so the bandwidth of the signal equals to what? So the number of the modulation index multiply n and multiply b. Okay? So here, this 2 is basically what? It's kind of the module. It's not called modulation index. It's what's it called? It's something RE. Do you remember that? We consider like QPSK, 16 QAM, right? It's like, you know, every symbol represented by a number of bits. So basically, in this case, this 2 basically means this guy, 0 and 1, okay? And this n times b, this n times b here, so basically means the bandwidth, okay? So basically, what we can see here is that we need n times b, so that is the bandwidth to transmit our signal, right? So basically, n times b means n times larger for PCM signal compared to the original signal. Okay? Yeah, hopefully this makes sense to you, but if it doesn't make sense, maybe we can recap a little bit how we can get this. Yeah, let me try to find. Oh no. Let's see, full screen mode. Yeah, so basically, this is what I'm talking about for the formula here, right? But we cannot directly use this formula here, so because now here it's a bit tricky. So this small m here, so basically means, yeah, kind of it's behind. It's basically, so this small s in our case is basically 2. Okay, so one symbol in our digital communication is 0 or 1. So basically, this m equals to 2. Okay, and the rest of it will give you the bandwidth. Okay, and the rest of it we have is n times b. So that's why we need nb for the bandwidth. That clear? Right. So basically, when we talk about this, we just say we're going to transmit the value there directly. But here, so we convert the value into a bit stream and then transmit the bit. Right. It's a little bit confusing, but hopefully yeah, you can, yeah, we can get it. So basically, this is the formula that I'm using. Does that make sense? Okay, great. Yeah, so in order to illustrate that, so I'm going to give you 2 examples. So you can see this is the big disadvantage of the digital communication, right? So we can somehow understand this, right? So for example, right? So yeah, let's say here, right? So for one value here, right? There should be just one waveform, right? But now instead of one waveform, so we kind of use 3 waveforms here to transmit. So that's why it's not efficient, right? Does that make sense? Okay. So let's see. Yeah, we're going to see some numbers here. So basically, for this kind of modulation, PCM, so we have 2 important applications. So one application is called plain old telephone service or POT. So anybody heard of it? Yes, the old telephone system. Okay, so yeah, let's see how it works. So basically, it's a telephone, right? So basically, what we do is that our input is a voice signal. Okay, that's our input. And then basically, we have some very simple filtering operation to filter this signal out. We have LPF. So with the cutoff frequency, so that will be the bandwidth of this guy, right? So basically, the bandwidth of this guy is 3400 hertz or 3.4 kilohertz. Okay, so this is basically the cutoff frequency. And then, so we do the PCM operation, right? We sample it, and we quantize it. Okay. So here, let's say, so if it's like 34 or 3.4 kilohertz, so what should be the sampling rate? Yeah, 2 times that, right? So 2 times that is like 6.8K, right? So here, so because of the imperfection of this low pass filter or whatever, normally we give a little bit of room there, right? So we use 8K sampler. Okay, so we have 8K samples per second, right? So that's our sampling. And then in order to represent each of the samples, we use 8 bits. So we have 8 bits per sample, right? So here basically it means that here this n equals to 8, right? So we have 8K samples per second and 8K bit. Then the output is like 8K times 8, right? We have 64K bits per second, right? So that is basically the bit rate for our voice, right? So this number, you should remember it. So that's very, we probably will use that all the time, right? And now let's compute the bandwidth, right? So basically for the bandwidth of this guy, so we divide everything by 2 here, right? NB would be our bandwidth, right? 64 kilobits divided by 2 is what? 32K hertz, right? And remember, the original signal has like 3.4K hertz for the bandwidth, right? But now, in order to transmit this using PCM, we need 32K for the bandwidth, right? So this is the bandwidth, right? So that is like almost 10 times higher of the analog signal, right? Okay, so it seems very inefficient. And now let's see a second example, so which is a compacted disc or CD. Yeah, who heard of it? Nobody? Really? Did you use that before? Really? Oh, yeah, I think I used that maybe like, the last time I used it is in 2002. Yeah, that is like 22 years ago. Oh my. Yeah, I have a machine, Sony, so which is very nice. But let's see how this works, right? So basically, it also uses PCM. So basically, what it do is that so we have a music signal as our input, right? And then we do the same procedure there. We have LPF, and then we have a color frequency here. So that is music. So we have a little bit higher bandwidth, 20K. Okay, and then we do the same thing, right? We sample it and quantize. Okay, so now let's see the rate here, right? We have 20 kilohertz here. So basically we double it, that's 40, right? But here we use a little bit higher. We use 44 times 1 kilohertz. Yes, for the sampler. So we have 44.1 samples per second. Samples per second. And then here, because it's music, right? So we need higher precision here. We use 16-bit per sample to represent each sample here. Then we'll multiply these two together. So basically, what we got here is 705.6 K bits per second. Okay. So normally, bits per second, we write that as BPS, right? That means bits per second. Okay, so this is the amount of the bit rate, right? Then we divide it by 2, so we get for the bandwidth, so we get about 303 kilohertz, right, for the bandwidth, and then compared to the original bandwidth here, right? So here we need about 15 times. Okay, compared to the original analog signal, right? You can see this seems not efficient way for the communication. Okay, that makes sense? Okay, yeah, there are a number of ways to solve the problem, right? It's not a big deal in the end, right? Because now, yeah.
Why'd you divide by 2?
Yeah, because of this.
Oh, okay, gotcha.
Yeah, NB is the bandwidth. Yeah, good question. All right, so yeah, you'll see later that there are so many ways to deal with this kind of problem. In the end, it's not a big problem. Yeah, because although for the voice, we say we need 64 BPS, right? In theory, but in practice, we need a number much lower than that. Why is that? Yeah, because most of our signal has loss of redundancy, right? For example, if we want to transmit a video, right? Probably, the difference between this frame and the last frame are very, very small. Okay, so we can, just, transmit the difference between the two frames, right? That will reduce the bit a lot, right? For example, if the sky is blue, right, it is probably will be blue for a sequence of frames, right? We only need to transmit blue once, right? We don't need to transmit every time, right? There are lots of room for compression, so basically we can reduce the bit rate significantly. Okay, so now let's see the next topic. So that is the advantages of digital communications, right? We see some disadvantages, right? Yeah, and we're gonna see some advantages, and then we're going back to see the disadvantages, or how can we overcome the disadvantages, right? So for the advantages of digital communication, so we kind of go over them before roughly, but let's go over them again. So basically, a big advantage for the digital communication, so this one is one of the most important things, right, is the ability to deal with the noise. Okay, so as we said before, so for analog communication, so the noise will appear in the received signal no matter what, right? There's no way to get rid of the noise. Do you agree? Right, because for example, for the amplitude modulation, right, when we transmit that over the air, there will be some thermal noise or whatever other noise added on the top of it, right? So in the receiver, there's no way to recover the exact original signal, right? We can recover something look like that, but we cannot recover exactly like that, right? But for the digital communication, if we transmit a bunch of bit streams, we can, right? As long as the noise is not big enough, it's not very large, then we can recover exactly what we transmit, because what we transmit is just 0 and 1s, right? If we receive like 1.5, we think, okay, that might be a 1, right? If we receive like 0.1, that might be a 0, right? We can map this to 0 and 1s. So it is possible that we can transmit exactly, so we can receive exactly what we transmit, right? Does that make sense? According to this, so there's a common belief, I think it's before 1948, that no matter what you do, even for digital communication, so there's no way that you can receive what you transmit with 100% probability. Right, as we said, right? So what you receive depends on the noise, right? So if the noise is higher, then let's say if we add a random noise on some signal, right? So there's always a chance that if we transmit a 1, if the 0 is -1, but if the noise is -1, then you receive a 0, right? You may think that is a 0, not a 1. Then you made a mistake, right? So a common belief is that no matter what you do, there's no way that you can receive what you transmit for sure. There's a probability of failure. There's always a probability of failure. Does that make sense? You agree with that? So that's what people believe before 1948. It basically means that it's not correct, right? So we can actually do something very smart to make sure that we can receive what we transmit correctly with 100% probability. There's no any chance of error, right? So counterintuitive, right? So actually we can do it, right? The secret of it is coding that we're going to talk in another slide, okay? Kind of not intuitive. So yeah, this is another super important property of digital communication is we can do compression, right? Although we have way more bandwidth, right? N times B, but the way to deal with this, one way to deal with this problem is to do the compression. There's so much redundancy in the source signal. So by the way, regarding the previous one, I forgot to mention. So the way to receive the signal with 100% probability is, so this was told by Shannon, Claude Shannon, so the father of information theory, right? So he tells us, you can always achieve that as long as you follow what he suggests, okay? And also, the father of compression is also Claude Shannon, and he tells you, okay, so what is the fundamental limit of how much bit you can compress for a source? Okay, so he's kind of father of many things. Also, some people believe he's the father of AI as well, because he have this famous maze. Did you heard of it? So he built a maze, and let a mouse inside, and then artificial mouse, and then the mouse can eventually figure out how to get out of the maze, right? So that's a kind of old version of one example of artificial intelligence. Anyway, yeah, so the key thing here is that we can compress, right? We can get rid of the redundancy of the information. Now, for example, as our telephone system, right? So typically, 64 kbps is what, should be BPS, right? The typo here. So it's what we expect, but in practice, it's obviously less than 10 kbps, okay, after compression. You can see, so we can reduce the redundancy by a lot. Okay, and another advantage of digital communication is about security, right? We can do encryption. So encryption basically means that, we can, kind of change our source information to something else. Maybe, for example, we can add a random sequence on top of it, or and pass it to another function, to make it, secret. Okay. And we can also do scrambling. So scrambling basically means that So it's not as strong as encryption, but it's also kind of a layer of security. So basically, so disregarding to the case where we don't want to transmit a sequence of 0 or a sequence of 1, right? If we do that, there may be many problems for synchronization, for other kind of problems, right? So we can do scrambling, right? So basically, that can make the signal, look like a random sequence. Okay, so that's that can be a form of secure communication as well, right? But for analog communication, we cannot really do it, right? Also, and the other thing is that nowadays many sources are already digital; they're not analog anymore, right? Yeah, voice and video, I mean voice. I think music, they're analog by nature, right? But nowadays, many sources are not analog anymore. For example, for the image, right? Before we used film, but now everybody using digital camera, using our phones, right? They are digital by nature, right? So if they're digital by nature, why we want to use analog communication, right? We just treat them as bits and then transmit, right? So and the other thing is that for the digital communication, it's easier to store, right? For the analog signal, it's harder to store them. Okay. Yeah, for example, so anybody have seen this video tape or music tape? No, yeah, probably you're too young for that, right? When I was little, so when I watch a video or film, then I have a big tape, right? I have to put that in this big box and then watch it on analog TV, right? But as time goes by, it will fail, right? It will not last for like 20 years. It may last for a few years, and then you hear lots of noise on the audio and lots of noise on the video. You can really see it. So there's a degradation in terms of quality. But for digital content, it will be much better. Okay, still have the degradation, but it will be much better. Okay, and we can add protection on top of it. Okay, and this is what we talked a little bit about before. So basically, it's information agnostic, right? So basically, it sort of doesn't matter what we really transmit, right? So we can use the same communication technology to transmit different information, right? For example, we can just use Wi-Fi to transmit voice, like voice over Wi-Fi, right? And then we can use Wi-Fi to transmit video. Okay. Of course, the requirement of the bit rate may be different, but in terms of modulation, there's no big difference, right? But for analog communication, if you still remembered, right? So we'll give you some example of how we use like AM to transmit the audio, the music, right? Then we need to transmit the mono part, and then we need to transmit the stereo part in a different way. Even with different, some part we need to use like DSP, and some part we need to use something else, right? Like USB, LSB, and so on. So we need to for those analog signal, we need to use a very specific, customized communication technology to transmit each of them, right? But for digital communication, we sort of don't need to do that. Okay. And the other thing is for the efficiency, right? So for the multiplexing, right? For analog communication, the only kind of multiplexing we have seen is in the frequency domain. We have frequency division, multiple access, and the frequency division duplexing, right? So, but for digital communication, we can do duplexing or multiplexing in many domains, right? Like in time domain, of course, we can do that in the frequency domain, like what we're doing now. And we can also do that in the so-called code domain, right? So basically, we can use, it's hard to explain, but it basically means that, so my signal and your signal can communicate at the same time, same frequency band, but using different signal shapes. And these two shapes are kind of orthogonal to each other, right? And then you can decode them simultaneously at the receiver. Okay, so this is called code multiplexing, right? So it's better for efficiency. And the other thing is reproduction and the regenerative repetition. As we said, right? So we can regenerate the digital signal exactly because it's all 0 and 1s, right? But we can now do that for analog signal. right? Because it's always be noisy. Okay, so and another important property is that if we're willing to do more complex stuff, we can get a better performance, right? This is why we have like Wi-Fi from 1 to 6E now, right? And this is why we have from 1G to 5G for the cellular communication, right? If we pay more for the complexity, then we can improve, the data rate and other metrics, right? So we can see the data rate improved significantly from Wi-Fi 0 until Wi-Fi 0 is only 1 to 2. Oh, okay, until now, right? This is now. Okay, you can see we have a huge improvement. Okay, as long as you want to pay some complexity. Okay, so yeah, let's discuss that in the beginning of next lecture. So here, basically, we're going to talk about what are the desirable properties for digital communication and some disadvantage of it and how it is possible to overcome these disadvantages. Okay, yeah, thank you.